Towering peaks, deep valleys, ancient glaciers, and seemingly immovable walls of rock have long given the Swiss Alps an image of permanence. Generations have looked at these mountains as symbols of stability, landscapes that change only across geological ages rather than within a human lifetime. Yet a growing series of fractures appearing across parts of the Alps is forcing a closer examination of that assumption. Why are large cracks emerging on mountain slopes that appeared stable for centuries? Why are entire sections of alpine terrain now being monitored around the clock? And why are authorities increasingly concerned that visible fissures may represent only the surface expression of much larger movements occurring deep within the mountains themselves? The questions have gained urgency because some of the most significant cracks currently under observation are not isolated fractures in exposed rock. They are signs of broader slope deformation affecting large volumes of earth and stone. In several locations across Switzerland, mountain flanks are shifting, stretching, and weakening in ways that are measurable from day to day. The phenomenon has become one of the most closely watched natural hazard issues in the country, particularly in the canton of Valais, where steep terrain, changing climate conditions, retreating glaciers, and unstable geological structures intersect. Among the sites attracting the greatest attention is the Les Fissures slope above the Navissance Valley in the Val d'Anneviers region. Here, a major fissure has developed across the mountainside, extending roughly 250 to 300 meters, equivalent to approximately 820 to 980 feet. While the crack itself is visually striking, its significance lies less in its appearance and more in what it reveals about the movement of the slope beneath it. Measurements indicate that sections of the affected terrain are continuing to move, with expansion rates measured in millimeters per day. Such movement may appear insignificant when viewed over a 24-hour period. Yet over weeks and months, those small increments accumulate. More importantly, the ongoing displacement confirms that the slope remains active rather than dormant. The mountain is not merely displaying a static scar, it is undergoing deformation. The estimated unstable volume associated with the Les Fissures sector is approximately 500,000 cubic meters, or about 654,000 cubic yards. To visualize that quantity, imagine a mass of earth and rock capable of filling hundreds of Olympic-sized swimming pools. The concern is not simply that a crack exists, but that such a volume may eventually move if instability progresses. Further complicating the situation is the appearance of secondary fractures. These additional cracks suggest that stress is being redistributed through the slope. Rather than a single fracture accommodating movement, multiple zones are showing signs of strain. Such patterns often indicate that deformation is affecting a broader section of terrain than the visible primary fissure alone would suggest. Swiss authorities have therefore focused significant monitoring resources on the area. Modern slope surveillance extends far beyond traditional visual inspections. High-precision instruments track displacement rates, detect subtle ground movements, and help identify acceleration that could signal changing conditions. Satellite observations, aerial surveys, and ground-based measurements collectively provide a detailed picture of how the mountainside behaves over time. One reason this monitoring is considered essential is the location of the slope relative to the Navissance River below. If a substantial landslide were to occur, debris could potentially obstruct the river channel. Such natural blockages have historically produced secondary hazards in mountainous regions. Water accumulating behind a landslide dam can create temporary lakes, whose eventual failure may generate destructive downstream flooding. For communities farther along the valley, this possibility introduces a hazard chain extending beyond the initial slope failure itself. Authorities therefore evaluate not only the stability of the mountainside, but also the potential consequences for river systems, infrastructure, transportation corridors, and settlements located downstream. The heightened attention surrounding Val d'Anneviers does not emerge in isolation. It reflects a broader pattern increasingly observed across the Swiss Alps. Numerous mountain regions are exhibiting signs of changing stability conditions. Some involve visible cracks and fissures. Others manifest as rock falls, debris flows, gradual slope movements, or structural changes associated with shrinking glaciers. One of the most important developments affecting alpine terrain involves the retreat of glaciers. For thousands of years, vast masses of ice occupied valleys and mountain flanks throughout the Alps. Beyond their role as frozen reservoirs of water, glaciers exerted immense physical pressure on the landscapes surrounding them. In many locations, the ice acted as a stabilizing support against adjacent rock slopes. As glaciers shrink, that support diminishes or disappears entirely. Slopes that were previously buttressed by thick ice are left to adjust to a new physical reality. The process does not automatically trigger collapse, but it alters the forces acting upon mountain walls. In some cases, geological structures that remained stable under glacial conditions may begin responding to the removal of that support. The significance of this process became dramatically apparent in the Lötschental region. During a major mountain and glacier collapse event, enormous quantities of material descended into the valley, producing one of the most consequential alpine slope failures in recent Swiss memory. The scale of the movement involved millions of cubic meters of rock, ice, and debris. The event demonstrated that mountain instability can no longer be viewed solely through the lens of isolated rockfalls. Entire slope systems may evolve over time before reaching critical thresholds. Visible fractures, increasing deformation rates, and progressive weakening can all form part of a longer sequence that culminates in large-scale failure. The lessons drawn from that collapse continue to influence how other potentially unstable locations are evaluated. Areas displaying growing fissures are now examined not only for their immediate conditions, but also for how they compare with previous examples of slope evolution elsewhere in the Alps. Another factor receiving increased attention is the condition of permafrost. High elevation regions of the Alps contain ground that historically remained frozen throughout the year. This permanently frozen material occupies fractures, pores, and spaces within rock masses. In effect, it has acted as a binding agent helping maintain the integrity of steep mountain walls. As temperatures rise over extended periods, permafrost can thaw. The loss of ice within fractures changes the mechanical behavior of rock formations. Blocks that were previously locked together may become more susceptible to movement. Small shifts can gradually evolve into larger instabilities, particularly where geological structures already contain weaknesses. The relationship between permafrost degradation and slope instability has become increasingly important because many alpine peaks exist near temperature thresholds where relatively modest climatic changes can produce significant effects underground. The visible consequences may not emerge immediately. Instead, years of gradual warming can weaken mountain structures before signs appear at the surface. Heavy rainfall represents another element influencing slope stability. Water entering cracks and porous materials increases weight and alters internal pressures within a slope. Saturated soils and fractured rock masses often become more prone to movement. In steep terrain, prolonged or intense rainfall can accelerate processes already underway. The interaction between rainfall, glacier retreat, and permafrost thaw creates a particularly complex hazard environment. Rather than operating independently, these factors often overlap. A slope weakened by long-term geological and climatic changes may become more sensitive to extreme weather events. Conversely, intense rainfall may reveal vulnerabilities that have been developing unnoticed for years. Evidence of these broader patterns extends beyond Val d'Anneviers and Lötschental. In the Crans-Montana region and other parts of central Valais, authorities have monitored repeated deformation zones affecting hillsides and infrastructure. These areas do not necessarily feature one dominant crack drawing international headlines. Instead, they consist of networks of unstable terrain where gradual movement remains under observation. Such locations illustrate an important reality about mountain hazards. Instability often develops as a distributed process rather than through a single dramatic fracture. Small cracks, subtle ground displacement, minor rockfalls, and localized deformation may collectively indicate broader structural changes occurring within a mountainside. The Swiss Alps have always been dynamic landscapes shaped by tectonic forces, erosion, weathering, and glaciation. The mountains themselves owe their existence to the collision of continental plates that uplifted vast quantities of rock over millions of years. Movement and change are therefore intrinsic features of alpine geology. What distinguishes current concerns is the growing evidence that some destabilizing processes may be accelerating within certain regions. Monitoring systems are revealing movements with a level of precision unimaginable only a few decades ago. Researchers and hazard managers can now detect millimeter-scale changes across large areas, track evolving crack networks, and analyze deformation trends in near real time. These technological advances provide valuable early warning capabilities, but they also reveal just how active some mountain slopes have become. Across Switzerland, the appearance of major fissures has therefore become more than a local geological curiosity. Each crack offers a visible reminder that the Alps are living landscapes undergoing continual adjustment. Beneath the spectacular scenery that attracts millions of visitors every year, powerful natural processes continue reshaping the mountains, often at rates that are only now becoming fully measurable. The challenge facing authorities is not simply identifying where movement exists, but determining how that movement may evolve. A crack visible on the surface is often the final expression of stresses that have been accumulating throughout a much larger body of rock and sediment. In slope mechanics, fractures rarely appear without cause. They develop because materials are stretching, separating, rotating, or settling in response to forces acting within the mountainside. This distinction is important because the dimensions of a visible fissure can sometimes underestimate the scale of the underlying instability. A crack measuring several hundred meters across the surface may be connected to a deformation zone extending far deeper underground. The visible opening becomes a marker of movement rather than the entirety of the problem itself. At Valais, the continued expansion of the Les Fissures fissure has therefore attracted attention not because of its width alone, but because it demonstrates that deformation remains active. Every additional millimeter of displacement provides information about the condition of the slope. A stable crack that stops growing presents a different risk profile than one that continues to lengthen, widen, or generate secondary fractures. The appearance of multiple cracks is often particularly significant. When new fractures begin forming near an existing fissure, it may indicate that stresses are spreading through a broader section of terrain. Instead of movement being confined to one narrow zone, larger portions of the slope may be adjusting. Such developments are carefully documented because changes in crack patterns can reveal evolving conditions that are not immediately visible through casual observation. Mountain instability is frequently described as a progression rather than a single event. In many cases, years or even decades of gradual deformation precede any major slope failure. Tiny movements accumulate. Fractures expand incrementally. Water infiltrates newly opened pathways. Geological structures respond to changing forces. By the time a significant collapse occurs, numerous warning signs may have already appeared, although interpreting those signs accurately remains one of the most difficult challenges in hazard management. The Swiss Alps offer countless examples of landscapes shaped by earlier collapses. Many valleys contain deposits left behind by prehistoric landslides whose volumes exceeded anything recorded during modern history. Entire mountainsides have failed in the distant past, leaving scars that remain visible thousands of years later. These geological records demonstrate that large-scale slope failures are not anomalies within alpine environments. They are part of the natural evolution of steep mountainous terrain. What has changed is the level of exposure. Modern transportation networks, settlements, hydroelectric facilities, tourism infrastructure, and communication systems occupy valleys that were once sparsely populated. A slope movement that might have attracted little attention centuries ago can now carry far-reaching consequences because of the interconnected nature of modern society. Roads winding through narrow valleys often have few practical alternatives. Rail connections frequently follow the same corridors. Rivers serve as critical components of water management systems. Power infrastructure crosses mountainous terrain to connect regions separated by high peaks. As a result, even relatively localized instability can affect transportation, energy distribution, tourism activity, and economic operations far beyond the immediate area of concern. The canton of Valais illustrates these realities particularly well. Surrounded by some of the highest mountains in Europe, the region contains numerous communities situated within narrow valleys beneath steep slopes. The geography that creates breathtaking alpine scenery also concentrates people and infrastructure in areas where natural hazards must be carefully managed. Hazard mapping has consequently become an essential component of Swiss planning. Detailed assessments identify areas exposed to landslides, rockfalls, avalanches, floods, and debris flows. Construction standards, land use decisions, and emergency planning are informed by these evaluations. The objective is not to eliminate natural hazards, an impossible task in mountain environments, but to reduce vulnerability through informed decision-making. The growing fissure at Les Fissures represents exactly the type of situation these systems are designed to address. Continuous monitoring allows authorities to track developments and prepare response measures if conditions deteriorate. Evacuation planning, infrastructure assessments, and contingency strategies can be developed long before any critical threshold is reached. Such preparations reflect an understanding that uncertainty remains unavoidable. Geological systems do not operate according to precise schedules. A slope may remain relatively stable for years despite visible cracking. Another may experience accelerating deformation over a much shorter period. Forecasting exact outcomes remains difficult because mountain environments involve countless interacting variables. Rock type, fracture orientation, groundwater conditions, slope geometry, weather patterns, vegetation cover, and climatic influences all contribute to stability. Small differences in these factors can produce markedly different results even between neighboring slopes. Consequently, hazard assessments often focus on probabilities, trends, and scenarios rather than absolute predictions. The broader alpine region is increasingly becoming a laboratory for observing these interactions. Across Switzerland and neighboring countries, researchers are documenting changing conditions in high mountain environments. Rockfalls have become more frequent in some locations. Glacier retreat continues exposing terrain that remained ice-covered for centuries. Permafrost degradation is being observed at elevations where frozen ground was once considered reliable. Many of these changes unfold gradually enough that they escape immediate notice. A glacier may retreat only a short distance during a single season. A crack may widen by mere millimeters over several days. A rock wall may experience subtle shifts detectable only through instruments. Yet when these processes are viewed over years and decades, the cumulative transformation becomes striking. Photographs taken generations apart reveal valleys dramatically altered by shrinking ice. Former glacier surfaces now support vegetation. Newly exposed rock faces display fresh fractures. Meltwater streams occupy channels that did not previously exist. In many locations, landscapes are adjusting to conditions not experienced since before the expansion of modern glaciers. These adjustments do not automatically translate into catastrophic outcomes. Most unstable slopes do not become disasters. Many continue moving slowly without reaching critical failure states. Some eventually stabilize. Others shed material through smaller rockfalls and landslides that gradually reduce accumulated stress. The presence of a crack alone is therefore not proof that a major collapse is imminent. Nevertheless, visible fissures demand attention because they provide evidence that change is occurring. Mountains often reveal their condition through such indicators long before larger events take place. Ignoring those signals would mean overlooking some of the most valuable information available regarding slope behavior. The recent collapse in the Lötschental region reinforced this lesson. Large failures rarely emerge from entirely unknown conditions. In many instances, precursory signs exist, including deformation, cracking, rockfall activity, and measurable movement. The challenge lies in distinguishing between slopes that are simply adjusting and those progressing toward more serious instability. That challenge becomes even greater when climate influences are incorporated into the equation. Rising temperatures affect glaciers, snow cover, water availability, and frozen ground. Changes in precipitation patterns influence erosion, runoff, and groundwater conditions. These environmental shifts interact with geological processes in ways that are still being actively documented. The Swiss Alps therefore occupy a critical position in discussions about mountain hazards. Their extensive monitoring networks, advanced scientific capabilities, and long history of hazard management provide valuable insights into how alpine landscapes respond to changing environmental conditions. Observations collected from locations such as Valais contribute not only to local safety efforts, but also to broader understanding of mountain stability worldwide. Beyond Switzerland, similar concerns are emerging in mountain regions across Europe, North America, Asia, and South America. Retreating glaciers, thawing permafrost, and changing precipitation regimes are influencing landscapes from the Rocky Mountains to the Himalayas. The processes observed in the Alps are part of a larger pattern affecting high-elevation environments around the globe. Yet the Swiss examples remain particularly compelling because of the precision with which they are monitored. Few mountain regions possess such dense networks of instruments capable of detecting minute changes. This level of observation allows authorities to identify trends that might otherwise remain hidden until more dramatic manifestations occur. For residents living in alpine valleys, the growing cracks are reminders that mountains are not static monuments. They are evolving geological systems shaped by forces operating on timescales ranging from seconds to millions of years. Rock continues to fracture, valleys continue to erode, slopes continue to adjust. The landscape visible today represents only one moment within a much longer process of transformation. The fissure at Les Fissures embodies that reality. Stretching hundreds of meters across the slope above the Navazens Valley, it serves as one of the clearest visible indicators of ongoing change in the Swiss Alps. Its continued growth has drawn attention because it highlights the connection between surface features and deeper geological processes operating beneath the mountainside. Viewed in isolation, a crack may appear to be little more than a fracture in the earth. Viewed within the broader context of alpine geology, glacier retreat, permafrost degradation, rainfall variability, and slope deformation, it becomes part of a far more complex picture. The fissure is not the phenomenon itself. It is evidence of the phenomenon. That distinction helps explain why the current situation is being monitored so closely. The concern extends beyond a single opening in the ground. It centers on understanding the condition of an entire slope system, the forces acting upon it, and the potential consequences if instability progresses further. Across the Swiss Alps, similar questions are increasingly shaping hazard assessments. Which slopes are adjusting normally? Which are becoming progressively weaker? How are glaciers, frozen ground, and changing weather patterns influencing mountain stability? Where might future deformation appear, and what indicators should receive the greatest attention? Clear answers are not always available. Mountains seldom provide certainty. They provide clues, cracks, movements, fractures, rockfalls, and subtle shifts that must be interpreted through careful observation. The expanding fissure in Valais is among the most visible of those clues at present, but it forms part of a wider pattern extending across alpine landscapes. Massive cracks appearing in the Swiss Alps are therefore not random anomalies scattered across otherwise unchanged mountains. They are signs of ongoing adjustment within one of the world's most iconic mountain ranges. Some are linked to slow-moving landslides. Others reflect deeper geological deformation. Many exist within environments increasingly influenced by glacier retreat, thawing permafrost, and evolving climatic conditions. The mountains remain standing, the valleys remain inhabited, and monitoring systems continue tracking every measurable change. Yet the growing network of fissures appearing across parts of the Alps carries a message that is becoming increasingly difficult to ignore. Beneath the enduring image of permanence, sections of the alpine landscape are actively reshaping themselves, 1 millimeter, one fracture, and one shifting slope at a time.